Welcome to the Explainer. Today, we're cracking the code of one of organic chemistry's absolute most versatile classes of reactions, the nucleophilic substitution of haloalkanes. If you've ever wondered how chemists take a simple, basic molecule and transform it into an incredibly wide array of complex functional groups, well, you're in the right place. We're going to look at the exact blueprints for these transformations. Let's get right into it.
Here's our roadmap for today. We'll be hitting 6 sections. 1. Meet the haloalkane. 2. The nucleophilic attack. 3. Building alcohols and ethers. 4. Ambident nucleophiles. 5. Expanding the carbon chain. And finally, 6. The big picture. Let's get started.
Section 1. Meet the haloalkane. Okay, let's dive into this by introducing the main character of our chemical narrative today.
To really understand these reactions, we first need to define exactly what we're working with. A haloalkane is, simply put, a halogen derivative of an alkane. Structurally, it's very straightforward. You take a standard alkane and you obtain a haloalkane by replacing one or more of its hydrogen atoms with halogen atoms. Things like chlorine, bromine, or iodine. And that simple swap of a hydrogen for a halogen, it completely changes the molecule's destiny.
And here is the fundamental reason why that destiny changes. When you bond a carbon atom to a halogen atom, which we represent here as the CX bond, that bond becomes highly polar. The halogen essentially pulls electron density towards itself, and that creates a sort of magnetic vulnerability in the molecule. Because of this extreme polarity, this bond easily undergoes dissociation. It's literally a prime, easy target for any reactive molecule looking for a place to attach.
Section 2, the nucleophilic attack. So we've got this vulnerable, highly polar bond. What happens next? Let's transition to the action phase of our explainer. The source material gives us this definitive quote, "So haloalkanes easily undergoes nucleophilic substitution reaction." Because that CX bond is so ready to break or dissociate, it sets the stage perfectly for a nucleophile. That's a nucleus-loving, electron-rich species. It comes in, attacks that carbon, and completely kicks out the halogen. The halogen is substituted right out by the nucleophile. And this simple mechanism, it's the core engine for every single compound we're about to build today.
Section 3. Building alcohols and ethers. Now that we actually know the mechanism, let's open up the builder's toolkit. By simply swapping out which nucleophile we use to attack the haloalkane, we can confidently build entirely new, useful classes of compounds. Comparing these reagents reveals just an incredibly systematic process. If we treat our haloalkane with an aqueous solution of potassium hydroxide or sodium hydroxide, that's aqueous KOH or NaOH, the product is an alcohol. But what if we change the reagent to a sodium alkoxide? Well, the product changes to an ether. We can also use silver oxide. If we use dry silver oxide, we get an ether. But if we use moist silver oxide, the water actually changes the chemistry to produce silver hydroxide in the mix, and our haloalkane becomes an alcohol. It's a highly predictable, beautifully organized system of chemical construction. So the absolutely crucial point here is that specific reagents yield specific guaranteed results. Take that reaction with sodium alkoxide, for example. When a haloalkane is treated with an alcoholic solution of sodium alkoxide, an ether is obtained along with a sodium halide byproduct. The specific reaction is so famous and so foundational in organic chemistry that it actually has its own official name. It's called the Williamson synthesis. Moving on to Section 4, ambident nucleophiles, two-faced attackers. We've seen how predictable this substitution can be. But now it's time to pivot and introduce a really fascinating plot twist in our chemical narrative. I want you to imagine a chemical attacker that isn't just a simple, single-point spear. What happens when the nucleophile rushing in to attack the haloalkane actually has two entirely different angles, or two different faces, that it can use to make that bond? The formal term for this from the notes is an ambidental nucleophile. By definition, this is a nucleophile which has more than one site, meaning more than one atom, available for bonding. The source text gives us two classic examples here. First, the cyanide group, negative CN, which can bond through either the carbon or the nitrogen. And second, the nitrite group, negative NO2, which can bond through the nitrogen or the oxygen. These are our two-faced attackers. Now, what's really interesting about this slide is how the metal paired with the ambident nucleophile completely flips the outcome. When we treat a haloalkane with an alcoholic solution of potassium cyanide, or KCN, the bond forms with the carbon atom, yielding an alkyl cyanide.
But if we simply swap the potassium out and use silver cyanide, AgCN, the attacker flips. No way, right? The bond forms with the nitrogen atom instead, yielding an entirely different compound, an isocyanide.
And this isn't just a one-off fluke either. We see the exact same behavioral pattern with the NO2 group. If our haloalkane reacts with aqueous potassium nitrite or sodium nitrite, KNO2 or NaNO2, the bond happens at the oxygen, giving us an alkyl nitrite. But react that exact same haloalkane with silver nitrite, AgNO2, and again, the bonding site flips. It bonds through the nitrogen, yielding a nitroalkane. It's just an incredible demonstration of how precise you have to be with your reagents to get the exact chemical pipeline you want.
Section 5. Expanding the carbon chain. Speaking of chemical pipelines, let's move to the next stage. We just learned how to create alkyl cyanides, but what amazing things can we do once we actually have them? How do we use them to expand and modify the carbon chain?
One direct path is reduction. Hitting an alkyl cyanide with complete reduction, meaning adding hydrogen across that triple bond, transforms the molecule directly into a primary amine. So you've successfully converted a haloalkane into a cyanide and now into an amine just by following the steps. Let's move to and see how this builds even further with hydrolysis, creating a really beautiful cascading chemical pipeline. Starting at step 1 with our alkyl cyanide, we introduce water in the presence of concentrated hydrochloric acid. This causes partial hydrolysis, which yields an amide. But if we change the conditions in step 3 and use dilute HCl instead, the alkyl cyanide undergoes complete hydrolysis, pushing right past that amide stage to result in a carboxylic acid. So depending on the concentration of your acid, you can stop the train at an amide or write it all the way to a carboxylic acid. Section 6. The big picture. We've covered a lot of individual, complex reactions today. It's time to bring all of this together to reveal the overarching lesson of this explainer. And this brilliantly illustrates the sheer unmatched versatility of the haloalkane. From just one single type of starting material, a basic alkane with a halogen attached, we have successfully built alcohols, ethers, cyanides, isocyanides, nitrites, nitroalkanes, amines, amides, and carboxylic acids. We didn't need entirely different starting blocks for each of these. We just used nucleophilic substitution as our master key. It really makes you think, doesn't it? We've seen how the highly polar, easily dissociated CX bond acts as a gateway to almost every major functional group in organic chemistry. So I'll leave you with this provocative thought. If a single polar carbon halogen bond unlocks this much chemical potential, what other vulnerable, easily exploited bonds out there in organic structures just waiting for the right nucleophile to come along? Keep exploring, keep learning, and we'll see you in the next explainer.